RSA Cryptography Methods, and it is by Siddharth Lakshmisha. Me, of course. An introduction. Cryptography is the study of encrypting and decrypting messages. This paper covers various ciphers. Ciphers are methods of encryption like the Caesar cipher, Hill cipher, Enigma, RSA, etc. It also mentions the defects in each cipher and the qualities of RSA. It also covers various methods to avoid cryptanalysis, that is a cryptanalyst just breaking into your cipher, and frequency attacks using the frequencies of the letters in your English alphabet to block your cipher. Some prerequisites: modular arithmetic and inverses, Euler's totient function, exponent rules, operations and inverses of matrices, determinants of matrices, Euler's theorem, the GCD and the Euclidean algorithm, Bezout's identity, and Carmichael numbers. Some definitions and some notations. We define AB as the greatest common divisor of A and B, that is GCD of A and B. Example, GCD of 12 and 18 is 6. Phi n, Euler's totient function, the number of positive integers less than n and are co-prime to n. Example, phi of 7 is 6. A is congruent to B mod n. We learnt it in today's class. A minus B is divisible by n. That is phi. Example, 5 is congruent to 3 mod 2 because 5 minus 3 is divisible by 2. If and only if, IFF, A is equivalent to B where A and B are propositions, if A then B and if B then A are true. Z, the set of integers. Example, Y and Z. In a set. For example, X is in a set A. Det A, the determinant of matrix A. Carmichael numbers. If C is a Carmichael number, then A to the C is congruent to A mod C for all positive integers A. Now here are a few theorems that we will be discussing. Euler's theorem. A to the power of phi n is congruent to 1 mod n if GCD of A and n is 1. And Bezout's identity. There exists integers x and y so that ax plus by equals GCD of A and B. Actually go into the paper and what it says. Here is one of the ciphers, a Caesar cipher. This is a cipher where each letter of the message gets shifted by a specific value. For example, with shift value of 3 units to the right, M becomes P, N-O-P. So M becomes P, A becomes B, so on and so forth. The encrypting process is E of X is X plus B mod 26. As you can see, here are some encryption and decryption functions. This cipher indeed has a few defects. Encryption and decryption are symmetric processes. That is, if you have a shift value of 3 units to the right, decryption is 3 units to the left. A letter gets encrypted in the same way no matter where it appears in the text. So if you identify that so far M becomes P in the text, then for every M in the plain text, it will become P in the cipher text. 3. The search space is small. There are only 26 shifts. So you could just literally try out all the possibilities until you come across a message that makes sense. For example, if you come across the encrypted message JVTIVK, you could just try out all the possibilities until you find secret. Here we also talk about an extension. You could get more sophisticated by allowing scaling before shifting. As usual, the encryption process this time is AX plus B mod 26. For example, with E of x is 3x plus 2 mod 26. Paper is encrypted as XCXQD, you can see. The decryption function dy is A inverse times y minus b. You can actually see by trying to solve for x in the encryption function, you'll get 1 divided by A times y minus b, and 1 over A is A inverse in mod 26. This cipher this time has more search space. It's not that easy to crack as the Caesar cipher because you're going to scale it. This time it's 312 shifts. Though it has a problem. A letter gets encrypted in the same way no matter where it appears in the text. That also was a problem of the Caesar cipher. Number 2, the cipher can easily be attacked by frequency analysis. By frequency analysis, this is what it means. Some letters are used more frequently than others. E and A are the most common, whereas Z and J are not very common. So we can determine with reasonable confidence which 2 letters are E and A. And just like knowing 2 equations and 2 unknowns let us solve the equation, here knowing 2 values of the function tell us the encryption function. And because they are symmetric, it tells us the decryption function as well. Now we move on to another cipher, block ciphers. As the name suggests, it's a cipher where the letters are operated on in groups. Each group is converted to a vector. A vector is like it has only 1 column but a lot of rows. And that is multiplied by a matrix. And because of the matrix multiplication, the resultant product is also a vector, which gets converted back to letters. Here you can see an example right before your eyes. Say the matrix A is 3, 2, 1, 11. This message is separated into 2 blocks of 2. And each block can be viewed as a vector of numbers, as you can see. Multiply each by the matrix A. Of course, you have to take matrix A and A times the vector. You can't do the opposite, the vector times A, as that's the rule of matrix multiplication. The rows of matrix A and the columns of matrix B have to be equal. Now you basically turn each letter back into a vector. Each vector into a letter and get this. The paper. This is another thing to do with block ciphers. To decrypt a message, multiply each vector component by the inverse of matrix A. We can understand that because the inverse of matrix A times matrix A is the identity matrix, which can be regarded as 1. Now, when is it invertible? A 2 by 2 matrix with entries that are integers mod n turns out it only has an inverse when its determinant is invertible. You can see here, let A be the matrix. If A has an inverse matrix B, you take determinants on both sides. Det A times det B is 1 mod m. So det A has to be invertible mod m. Hence proved. The block cipher, we saw it's encrypted in blocks of 2, but it can also be encrypted in blocks of 3, 4, 5. If you get to multiply by its inverse to decrypt. Now we're really going to the topic of this paper, RSA. The encryption and decryption processes of RSA are not symmetric. Knowledge of encryption processes does not easily reveal the decryption process. You need 3 key ingredients to make it work. A modulus m, which is the product of 2 large primes. It may be even more large primes. Then phi m is p minus 1 times q minus 1. That's good. The encryption exponent e is greater than or equal to 1. So that GCD of e and phi m is 1. GCD of e and phi m has to be 1 as if, because it won't work as different things, different encrypted messages will show to the, will, when decrypted, will give the same output. So you need it to be equal to 1. And again, you can use the Euclidean algorithm for that. Then the decryption exponent, which is the inverse of the encryption exponent mod phi m. It can be found by Bezout's identity. Pretty easy. The numbers m and e are your public key, and p, q, and d are your private key. As suggested, the public key numbers can be kept public. Everyone can know about them. You can reveal it to the whole world. But P, Q, and D have to be kept private. The messages sent to you must be integers within 0 is less than or equal to x is less than or equal to m minus 1. If for longer messages, we can see what to do. In the last slide, someone who wants to send you the message x should send you x to the power of e this time. It's not multiplicative, it's the power of e mod m. To decrypt a message, compute d of y is y to the d mod m. You use e and d for encrypting and decrypting. Here is an example you can see below. If p is 43 and q is 97, then m is equal to 4171 and phi m is 4032. Since the GCT of 5 and phi m is 1, use e equals 5. Of course, other e's also work, but we are using e equals 5. A solution is d equals 161t. So ex is x to the 5 mod m and dy is y to the 1613 mod m this time. And these two are a pair. You encrypt using e of x, you decrypt using d of y. For instance, if x equals 24, you can just follow through the process to get the encrypted and therefore the decryption. The paper RSC again, but this time we need to show that encryption and decryption processes should undo each other. If they don't undo each other, we might get a wrong message. That's a problem for the receiver. So let's just find out. See, you have to find out d of e of x. Just compute absent-mindedly. You get this is equal to x to the ed mod m. And all we know is that ed is congruent to 1 mod phi m. And we need to, this is what you need to prove. If ed is congruent to 1 mod phi m, x to the ed is congruent to x mod m. As you can see, x to the ed is d of e of x, and that needs to be congruent to x mod m. Okay. So now here is the proof that this actually works. Write ed as a multiple of phi m, and ed is congruent to 1 mod phi m. So it can be written as phi m times something plus 1. And as you can see, you can write it as x times x to the phi m to the t. And now we split it into two cases. If GCD of x and m is 1, then x to the power of phi m is congruent to 1 mod m by Euler's theorem. So x to the ed has to be congruent to x mod m. This is pretty simple. But if GCD of x and m is greater than 1, we can't use Euler's theorem. But there's one thing we haven't used. M is the product of two primes. And since p and q are prime, for all integers x we have, if x times x to the power of phi m t is congruent to x mod p q, it should be congruent to x mod p and x mod q. This you can see. We know that phi m is equal to p minus 1 times q minus 1. So first we check this for x mod p. Now we split this also into two cases. If x is 0 mod p, then both sides are congruent to 0 mod p. As you can see, I'll just go backwards. Yeah, the left hand side is 0 mod p, right hand side is 0 mod p if x is congruent to 0 mod p. So that makes sense. And if x is not congruent to 0 mod p, typo again, then x to the power of p minus 1 should be congruent to 1 mod p by Fermat's little theorem. So x to the power of p minus 1 times q minus 1 to the power of t is congruent to 1 mod p. So we can see that that's congruent to x mod p. Similarly, you can prove it's congruent to x mod q. So we have thus proved that that encryption and decryption are the opposites of each other. That is, if you encrypt and decrypt at the same time, you get back the original. And now we can see. This theorem actually also holds if M is a product of more than 2 primes. As an exercise, you may check it. Now, if a spy wants to decrypt the message, he needs to find the decryption exponent. But we know that ED is congruent to 1 mod phi M. So that's the only way he can find the decryption exponent. But if you don't know phi M, there's no use in solving this equation. But now we prove that knowing phi M and the factorization of M are equivalent. Meaning, if you know phi M, you know the factorization of M and reverse. And there is actually no other way so far to compute phi M and therefore compute D. And if there was, you have to take all our money out of our bank account, because that can immediately be stolen. Theorem 3. Let M equal PQ where P and Q are different primes. If you know M and phi M, we can compute P and Q. This is actually pretty easy to prove using using quadratic equation. Phi M, if you expand, you get P minus 1 times Q minus 1 and continue expanding, you get N minus P plus Q minus 1. Now bring everything in terms of P plus Q. Because what we are aiming to make a quadratic equation with P and Q at the roots. So P plus Q, we need to know what P plus Q and PQ is in terms of M and phi M. We found P plus Q, PQ is M. So the x minus P times x minus Q, the quadratic equation is x square minus M plus 1 minus phi mx plus M. And the roots are P and Q. So you can easily find them using quadratic formula. Next. Now, what were we saying earlier? The messages have to be sent with 0 is less than or equal to x is less than or equal to m minus 1. Now, what happens if the message length is exceeding the modulus? Simple solution, break it into smaller parts. For a modulus m, let's just say the one flashed right there, it has 7 digits. So a message block should have 3 letters. So actually, if we have to assume that each letter is A 01, B 02 all the way until Z is 26. So it's a message block should have at most 3 letters because it has to lead to a number of at most 6 digits. For a modulus m is a bigger one right here, which has 8 digits but a leading pair of digits 12, which is less than 27. You should use a message block with at most 3 letters. Since if you have the letter N and N is encrypted as 14 and 14 is greater than 12. So 4-letter block that starts with N will exceed the modulus. And one more point, if E and phi M is greater than 1, I was talking about this also earlier, then the system does not work. For example, you can see the example flashed right on screen. E of 8 and E of 9 are both congruent mod M. And this is bad because different messages can be encrypted in the same way. And that is bad. Now, finally, in conclusion, the core of RSA is actually Fermat's little theorem, as we saw from this theorem 2 right here. We used Fermat's little theorem to handle the general case, even though we only used Euler's theorem. RSA is secure due to the difficulty of factoring huge numbers. If someone comes up with a quick way to like factor 400 digit or 1024 bit primes, semi-primes in very quickly, then we have to take all of money off our bank and be very cautious. Because if you know the factorization of M, you know phi M and you know D. And that is dangerous to the security. And finally, we saw that the encryption and decryption functions are both of the form A to the N is congruent to B mod M. And you need to solve that equation. We needed to solve that equation. And for that, it is actually crucial that N is relatively prime to phi M. Because if it is not, sometimes you'll get more than one solution. Sometimes you'll get absolutely no solutions at all. Thank you.
Harish sir, if you can give some feedback.
Just
Sir, you're on mute.
Now I could unmute. Sorry, I left the cell phone from where I had joined. Excellent presentation. I thought Siddharth did a wonderful job, and I was very happy to see the way he explained everything. Who was your mentor in this, Siddharth? Who helped you in the preparation?
Actually, are you asking in general for number theory?
Yeah, that also, plus specifically for this presentation.
Well, number theory, I actually learned most of it on my own, plus some help from my grandfather.
I see. Okay.
This presentation, I actually worked entirely on my own with no help.
Oh, excellent, excellent, excellent. You did a very, very good job. Very good job. A couple of suggestions that I have. So when you start the presentation, for example, you're talking about the RSA algorithm, right?
Yeah.
My suggestion would be to first try to communicate as soon as possible why this is such a big algorithm. You know, why this is a very big, important contribution in this field.
Yeah.
So that I think is very, very important. You have to hit it very early on in your presentation and not wait till your 7th slide or 5th slide. So first, you were setting up the problem, you were explaining the prerequisites and so on. But the first thing that should come up is, okay, what's the big issue? The big issue is whenever you are thinking about encryption, the encryption and decryption happens to be a symmetric process. But unfortunately, if it's a symmetric process, then it's easier to decrypt it because there aren't many combinations that you have to think through. And then you go on to this RSA algorithm saying that, but so we need to think about issues.
Actually,
yeah.
I have a little bit of problem here. I only cover symmetric ciphers at like around 6th slide or so.
Correct. No, so you don't even have to go into details of these two ciphers. But even if you do that, that's fine. But the biggest thing is you start the first slide, give an overview of why RSA algorithm is a very big thing, and then you go into the details. That's what I'm saying.
Okay.
Okay. But I could understand everything that you were explaining. I'm pretty sure that that's the case for the other students as well. They were able to follow what you were explaining, and you made it a point that you were explaining in a very simple way, and you have very good articulation. I don't have to tell you. You are very good at explaining, and you are very good at communicating your ideas. So that's a very big positive thing, and that doesn't come very easily. So you should keep it up, and you should continue on working on that skill. Very few people have that at your age. Okay, more than anything else, very few people have that in them in general. So you having in you at this age is a very big gift, I would say. And
Thank
and
you, sir.
yes.
Thank you, sir.
Yeah. Okay. So that's about it from my side. Any questions from the students? They please, I would suggest them to ask.
Okay, so since there are no questions, we'll move on to the next presentation. So Swasti is presenting next. So Swasti, are you ready with the presentation? Swasti, oh yeah, I need to. Yeah.
Yes, I am ready.
Yeah, can you share your screen and start the presentation?
Yes. Can you see my screen?
Yes, you can see the screen.
Okay, so we're going to discuss Euler's amicable numbers. And so let's start with the introduction. Amicable numbers are two whole numbers such that the addition of the proper whole divisors of one number is equal to the other number. So for example, if we have 220 and 280, the addition of the proper whole divisors of 220 is 280, and the addition of the proper whole divisors of 280 is 220. By proper whole divisors, what we mean here is that all the divisors of a number except the number itself. So for example, the proper whole divisors of 10 will be 1, 2, and 5. So only 3 such amicable pairs were known before the year 1700. 9th century mathematician Tabit ibn Qurra and the 17th century French scholars discovered two additional pairs, 17,296 and 18,416, and these two big numbers. So, and then Euler found 58 more pairs by himself. And before him, hundreds of mathematicians tried and found 3 pairs. How great is that? Euler published a paper containing a method to find amicable pairs. His method and its derivation are discussed in this paper. So the prerequisites are algebra, primes and composites, and functions. The definitions and notations discussed in this paper are, so the Euler sigma function is if n is a whole number, then sigma of n is the sum of all whole number divisors of n. So for example, if n is equal to 10, then sigma of n will be 1 plus 2 plus 5 plus 10. So the theorems discussed in the paper are, the theorem 1 is a number p is prime if and only if sigma of p is equal to p plus 1. For example, sigma of 7 is equal to 8, which is 7 plus 1. And theorem 2 is if p and q are different primes, then sigma of pq is sigma of q. For example, sigma of 3 times 5 is equal to 24. Sigma of 3 and theorem 3 is the extension of theorem 2. So if GCD of AB is 1, sigma of A sigma of A times sigma. Let's see the proof for theorem 1. The number P is prime if sigma of P is equal to plus 1.
Swasti, we cannot hear you. Swasti, are you back?
Yes, sorry, I was logged out. Yeah, so let P be a number such that sigma of P is equal to P plus 1. For any P, the divisors of P will include 1 in P. If P is composite, then P has at least one other divisor. So sigma of P is greater than or equal to P plus 1. Since sigma of P is equal to P plus 1, we can conclude that there are no other divisors of P other than P and 1. In other words, P is prime. Hence proved. Theorem 2, if P P and Q are different primes, then sigma of PQ is equal to sigma of P times sigma of Q. So the divisors of PQ are 1, P, Q, and PQ. Since P and Q are primes, there are no other fact divisors of PQ. So sigma of PQ is equal to PQ plus P plus Q plus 1, which is equal to P plus 1 times Q plus 1. And by theorem 1, P plus 1 times Q plus 1 is equal to sigma of P times sigma of Q. Hence 2. And okay, the proof for theorem 3 is let the factors of A and B be 1, A1, A2, A3, and so on until A. And the factors of B are 1, B1, B2, B3, and so on until B. So the factors of AB will be 1, A1, A2, A3, and so on until A. And then we are going to multiply B1 to all of these factors of A. So B1, B1A1, B1A2, B1A3, and so on until B1A. And then B2, B2A1, B2A2, B2A3, and so on until B2A. And then we have B, BA1, BA2, and so on until BA. Sigma of AB will be the addition of all the factors of AB. So sigma of AB will be 1 plus A1 plus A2 plus A3 plus so on until A, plus B1 plus B1 A1 plus B1 A2 plus B1 A3 plus so on until B1 A. And yeah, so on until B plus BA1 plus BA2 plus so on until BA. This is equal to, we can just take B1 out of this bracket. So we get 1 plus A1 plus A2 plus A3 plus so on until A plus B1 times A plus A1 times 1 plus A1 plus A2 plus A3 plus so on until A. And we're taking B out of this. So 1 plus A1 plus A2 plus so on until A. And then if you observe, this is the same as this is the same as this. So we can take this out of the whole expression. So we get 1 plus A1 plus A2 plus A3 plus so on until A, and 1 plus B1 plus B2 plus B3 plus so on until B. And this is equal to sigma of A. This is equal to sigma of B. Hence proved. So let's get into the paper now. So whole numbers M and N are amicable if and only if sigma of M minus M is equal to N and sigma of N minus N is equal to M. And sigma of M is equal to M plus N, which is also equal to sigma of N. So therefore sigma of M is equal to sigma of N. So now let GCD of M and N be A. Let P, Q, and R be prime numbers such that M is equal to APQ and N is equal to AR. Since sigma of M is equal to sigma of N, sigma of APQ is equal to sigma of R. Sigma of A times sigma of P times sigma of Q is equal to sigma of A times sigma of R. And we can just cancel this out. So sigma of P times sigma of Q is equal to sigma of R. And since P, Q, and R are prime, we can say that P plus 1 times Q plus 1 is equal to R plus 1. Now let X is equal to P plus 1 and Y is equal to Q plus 1. So XY is equal to R plus 1 and R is equal to XY minus 1. Since sigma of M is equal to N plus N, sigma of APQ is equal to APQ plus R, which is equal to A times PQ plus R. We also know that sigma of APQ is equal to sigma of A times sigma of P times sigma of Q, which is equal to sigma of A times P plus 1 times Q plus 1 because P and Q are prime. So A times PQ plus R is equal to sigma of A times P plus 1 times Q plus 1. And we can further simplify P plus 1 times Q plus 1 to XY. And PQ plus R will be X minus 1 times Y minus 1 plus XY minus 1. So sigma of A times xy is equal to a times 2xy minus x minus y. By this, Euler got y is equal to ax by 2a minus sigma of a whole times x minus a. This is equation 1. Let a by 2a minus sigma of a is equal to b by c. Observe that a is equal to b, a is equal to b. So if we substitute 2 in 1, the denominator will become cx minus b as given below. So y is equal to bx by cx minus b. So this a by a will become b here, and this 2a minus sigma of a will become c. So we have cx minus b. Now let's multiply both the sides by c. So cy is equal to cbx by cx minus b. And now let's subtract b from both the sides. So we have cy minus b is equal to cbx minus cbx plus b squared by cx minus b. And this is equal to cy minus b is equal to b squared by cx minus b. And this is equation 3. Now we are just 4 steps away. Start with the value a. Using equation 2, find b and c. Equation 2 is this, so you can find b and c. And then use equation 3 to find x and y, such that x minus 1, y minus 1, and xy minus 1 are all prime. Remember that x minus 1, y minus 1, and xy minus 1 are p, q, and r, which are prime. So yeah, and then x minus 1, y minus 1, and xy minus 1 are equal to p, q, and r respectively. And therefore, now we find the value of a times p times q and a times r. This is m and this is n. So, and therefore these two will be amicable. So the conclusion is that Euler was a genius enough to increase the stock of amicable numbers by a factor of 20, and he found a way to discover new amicable numbers. And a few possible extensions are, we took 3 primes, p, q, and r. What if we take 4 or 2 primes? How will it affect the final result? Yes, and that. Thank you.
Very nicely explained, Swasti. You did a very good job in explaining the entire idea of Euler. What I also liked is the possible extension that you provided. One thing I would have liked to see, I don't know, maybe it was a time constraint. If you could have walked us through one example and how Euler's ideas would have worked. What I want other students to see or think is there any connection between Euler's sigma function and Euler's totient function? Try to think if they are connected. I mean, if they are connected, it makes me less what you say intimidating when I look at Euler's works, because he has done so much work. I never have been able to understand how he, is able to come up with these ideas. And especially when you look at Euler's works, what I like about Euler's work is that they are easy for us to understand. I mean, it's not very difficult. But when you read through these ideas, you will get to see what an artist he was. He was more of an artist than a mathematician, so to say, in the sense that his ideas were so new at that point of time. He could come up with these brilliant ideas which no one else had thought about. And Swasti made a very good presentation of explaining one such idea, where you could see that there is a trial and error involved in it, but you can reduce the scope for trial and error by doing some nice algebra. And for that, you have to come up with a new idea, like he came up with this idea of sigma function. And that sigma function has so many nice number theory properties. you can prove a lot of nice properties about those sigma functions, and that is what helped him to prove these ideas. And if you see the substitutions that were getting carried out, at some point you may get lost in those substitutions. What exactly is Euler trying to do? So you can see that at one step there were three variables, and then he substituted those A, B, and C and converted into two variables of X and Y. That reduces your task of doing trial and error. So if you can bring out these small nuances in your explanation, that will make your explanation much more understandable for the audience to see why this substitution is going on. Because as when we are seeing, we can't connect those dots. Because you have seen this paper multiple times, you should be bringing it out to us so that we can see what you want us to see. Okay. And who helped you in this presentation? You did a very good job. Did someone else help, or you did
No, I
it?
did it on my own.
Very good, very good, very good, very good flow. I really like the explanation about sigma of AB is equal to sigma of A times sigma of B. I think that was brilliantly done when you listed down all the possible divisors of sigma of that number A, and you listed down all the possible divisors of B, and you did it beautifully. I don't think there would have been an easier way to explain how sigma of AB is sigma of A times sigma of B, because the other things are more or less the corollary from that. Sigma of P is basically sigma of P is P plus 1. You can just take it from that a sigma of AB. So I really like that explanation that you provided, and I'm very happy that you all are reading these papers that are not easy to read because they are quite technical in nature. All these notations and all, you have understood it brilliantly. And I also am very impressed that you guys are able to type these stuff. I don't know what software are you using. Are you typing this in PowerPoint, or you're using a different software?
PowerPoint.
Excellent.
Yeah, that's right.
Excellent. Because these are very, what you would say, frustrating notations when you have to really type. It takes so much time, and I'm very, very impressed by your efforts and ability to type these things.
Actually, you can just copy paste.
Copy paste from where?
Well, with the paper, in my paper, there was 5 functions that's not available in the standard set of keys. So you can either do one of two things. Number one, select the 5 function and put it in your paper, or just type 5 and check all the symbols.
Okay. So you did not use the equations that are equation builder in PowerPoint.
Yeah, there are equation build. I actually did use a little bit of equation builder in some of my things because it's impossible to get matrix without using equation builder.
I see. Okay. Very good. Brilliant presentations, both of you. Any questions from the students? Okay. It looks like other students are afraid that when they will present, someone else will ask the question. So we are not going to ask any questions. We are going to play like a team. We are not going to trouble each other. Okay, Sundar, how many presentations are we going to have today?
4 today and 3 tomorrow.
Okay. So let's proceed with the.
So
big hand for
Jayaditya,
Swasti as well.
So Jayaditya is going to present next. So Jayaditya, can you share your screen?
Yeah.
Yeah.
So my paper is about Fermat's last theorem for n equal to 4. So an introduction. Fermat, he had proposed a theorem called Fermat's last theorem, which states that there exists no x comma y comma z in natural numbers for n greater than 2, such that x raised to n plus y raised to n is z raised to n. And the proposition was first stated as a theorem by Fermat around 1637 in a margin of a copy of Arithmetica. Fermat added that he had a proof to it, but it was too large to fit in the margin. So now for more than 300 years, it continued to stay as a conjecture. Later on, it was finally proved by Andrew Wiles in 1994 and formally published in 1995. However, the proof to Fermat's last theorem in general is hard. And so in this paper, we will be looking at a special case of Fermat's last theorem, which is n equal to 4. So the prerequisites to this are solutions to the Pythagorean theorem. So if you have a Pythagorean triplet x squared plus y squared equal to z squared, then the solutions are x equal to m squared minus n squared, y equal to 2mn, and z equal to m squared n plus n squared. Given that the GCD of m comma n is 1 and m and n are not both odd. And then another prerequisite is the law of exponents and the law of squares, which states that if GCD of m comma n is equal to 1 and m into n is a square, then both m and n are perfect squares. And another prerequisite is the law of infinite descent. So if there exists a solution to an equation and there is a solution which is less than that, then the original cannot be a solution. Now the definitions. So a Pythagorean triplet. A comma B comma C is called a Pythagorean triplet for A comma B comma C belonging to integers. If A squared plus B squared equal to C squared, here A and B represent the perpendicular sides of the triangle while C represents the hypotenuse. The theorems in this paper are that x raised to 4 plus y raised to 4 equal to z raised to 4 has no solution for x, y, z belonging to natural numbers. So basically it has no solution in positive integers. So now the proof to it. So we use contradiction here. Assume to the contrary that there exists some solution to the equation. So let x, y, z be the solution to the equation with w. Okay, yeah. So with w taking the smallest value possible. So I've taken z to be w squared here. So x raised to 4 plus y raised to 4 is equal to z squared, which means that x squared whole squared plus y squared whole squared is equal to z squared. And then it is easy to note that x squared, y squared, and z form a Pythagorean triplet. So without loss of generality, we assume that y is odd. And in the prerequisites, we need to know the solutions to a Pythagorean triplet. And you substitute that here. So you get x squared is equal to 2mn, y squared is equal to m squared minus n squared, and w equal to m squared plus n squared for co-prime integers m and n are not both odd. But we know that w squared is m squared minus n squared. So if you add n squared on both the sides, you get w squared plus n squared is m squared. So again, they form yn, and m form another Pythagorean triplet. So again, you substitute possible values for y, n, and m because you know that they form a Pythagorean triplet. So you get y is r squared minus s squared, n is 2rs, and m is r squared plus s squared for co-prime integers r, s, and r and s are not both odd. So now we must note that m, r, and s must be co-prime. If they are not, then r and s could not be co-prime. So now x squared is 2mn. So you just substitute the value for n from here. So you get x squared is 4rsm. And then you can just substitute and solve, and you get that r will be a squared, s will be b squared, and m will be c squared for a comma b comma c belonging to integers. And then if you substitute these into the equation for m, this one, you get a raised to 4 plus b raised to 4 is c squared. But that contradicts the minimality of w, because w is greater than c. If you so basically w was m squared plus n squared, and then you manipulate and you get w is greater than c. Because of the contradiction, our assumption definitely must be incorrect, which implies that x raised to 4 plus y raised to 4 equal to z squared has no solution for x comma y comma z belonging to n. And because we knew that z is w squared, it proves that x raised to 4 plus y raised to 4 equal to w raised to 4 has no solutions in natural numbers. So in conclusion, we note that there exists no solution to Fermat's theorem for n equal to 4. And the possible extensions to this. So an extension to this proof is Fermat's last theorem for n equal to 3 and for some odd prime n. And a tougher extension to it would be Fermat's last theorem in general, which states that x raised to n plus y raised to n equal to z raised to n has no solutions in positive integers. Yeah, that's it. Thank you.
Very, very nice presentation. This paper was suggested by Manu. So the credit goes to him for selecting this paper. And I think it's a very nice paper because it gives you some insight into Fermat's last theorem and helps you to prove for a particular value at least. And also doesn't use that much difficult algebra, and helps you to link it to Pythagorean triplets, which most of us are aware. And you did a very good job in explaining these links very nicely. What I am curious about is, can the same approach be used for x to the power 2n, y to the power 2n, and z to the power 2n, where n is greater than or equal to 2? And can the same approach be applied to that? I don't know. I'm just thinking about that when you were presenting, which means you did a very good job because you made the audience think about, can this be used to understand for a more generic case than stopping at n equal to 4. So you mentioned about Andrew Wiles who proved this. I don't know if you remember or you heard about Manjul Bhargav's introduction. He was Andrew Wiles' student when he did his PhD at
He was
Princeton.
Andrew Wiles' student. I didn't know that.
Yeah, he did his PhD under Andrew Wiles. So that is his connection with that. And imagine how big this contribution is of Andrew Wiles, right? Because this theorem remained unproved for more than 300 years. And so you had to come up with new ideas because people have tried out different things. And remember that anything that Fermat had conjectured, Euler had proved most of the things. This was probably one of the things that Euler couldn't prove, or I don't know whether he even tried. When Jayaditya was presenting, I was thinking in my mind, is there any work of Euler that kind of talks about this aspect of Fermat's last theorem? And I don't think this was the last theorem proposed by Fermat. I think that it is called as Fermat's last theorem because this was the theorem of Fermat that remained unproved. So that was like calling, this is the Fermat's last theorem that we need to prove. So that's the context with which it is called as the Fermat's last theorem. So what now I am curious about is, what is the work that Euler has done in respect to this Fermat's last theorem in his work. Of course, he couldn't have got to the final thing because otherwise we would have known the work. But I'm curious, in that process of reaching to that point, what are the ideas that he tried, and do we have some evidence of his work in that direction? That would be interesting to know. See, the main idea behind these presentations is that we want to help you out to understand that, okay, these are the areas where I can read more. This is to make sure that we make you more curious and you go and read these papers. Another thing that I would highly encourage you to do, which I'm sure you might not have done by now, because you would have been so focused on your paper presentation, you might not have read other papers. So after the
I have
camp
read
or-
Swasti's.
because that was related to your paper somewhat. So it's not that much of a time investment to do. But what I encourage you to do is, after your presentation gets over or after the camp gets over, take access to all the papers that we have shared and read all of them. And if you carefully read all those papers, you will see that a couple of papers were always connected in those
Mine and Swasti's, for example.
Yes, and Jayaditya's and someone else's who will be presenting.
Sai Arun's and Jayaditya's.
Yeah, so we will be presenting on Pythagorean. It might have been a good idea to make Sai Arun present first, followed by Jayaditya.
Yeah, so the thing is, Manu was so Jayaditya is in Manu's group and Sai was in my group. So we didn't know that. So I didn't know that Jayaditya was going to present on this, and Manu maybe didn't know that Sai Arun was going to present on triple. So we couldn't schedule it that way. So
No, you could have swapped it later. No, how does it? Oh, so
Yeah,
Manu is
yeah.
not present today. That's why.
no. So basically,
Sorry.
I knew that Sai Arun was going to present on triplets, but I didn't know that Jayaditya was going to present on this paper, Fermat's last theorem, which was a continuation, which used triplets basically. So
Okay.
it kind of got.
Okay.
And we need to make sure that Amol presents last on 14th. So all the scheduling, so there were a bit of constraints which we needed to follow.
Got it.
Yeah. So
Very good. But I mean, Pythagorean triplets is something that people do know about. At least they know what is it, and the basic idea they know. Of course, Sai Arun's paper is going to go into much more detail, which is also nice. But that's a different paper. So yes, let's continue.
I think on the 13th, you can make Sai Arun present and then Jayaditya present or something like that.
yeah, we can do
If
that.
you have
And
time,
14th
go ahead.
we can swap. Yeah.
Yeah.
Okay, so the last presentation for today is by Raghav. So Raghav, if you can unmute and present.
One second. Can you see my screen?
Yes, we can. Yes.
Good afternoon, everyone. Today I'm going to talk about online bipartite matching. Introduction. Online bipartite matching is one of the first problems to receive attention of competitive analysis. The input for the problem is the bipartite graph G with sets U and V and edges E, where the vertices of U appear in an online fashion. That is, they appear one at a time. And the edges incident to the vertex U are shown when the vertex arrives. So we have to match U to a previously unmatched vertex V, and the decision is irreversible. The objective here is to maximize the matching. Prerequisites. Basic definitions related to graphs, edges, vertices, etc. The summation notation, induction, limit of 1 plus 1 over n to the power n, which is equal to E as n tends to infinity, and the geometric progression formula. Definition. Bipartite graph. A bipartite graph is a graph which can be divided into two disjoint and independent sets. Disjoint means the two sets have nothing in common, and independent here means that the sets that any two vertices in the same set do not share an edge. Notations. U is the part of the graph which comes in an online fashion. V is the part of the graph which is already given. We define n as the number of vertices in U. Ranking G sigma pi is the matching on input G with arrival order pi and permutation sigma done by the ranking algorithm. We denote ranking sigma as a short form to mean ranking G sigma pi. G pi sigma. We also assume that G has a perfect matching M asterisk from U to V. The ranking algorithm, the setup. First, we choose a random permutation that is an order or ranking sigma of the vertices of V. Now the matching. So when the vertex U of the graph U arrives, we define n of U to be the neighbors of U that haven't been matched yet. If n of U is not empty, then we match U to a vertex V in n of U such that the rank of V is minimum, that is sigma of V. The theorem. The ranking algorithm has a competitive ratio of 1 minus 1 over n plus 1 to the power n, which is asymptotically 1 minus 1 over e. That is when n tends to infinity. Lemma 1. Let X be a vertex in G. We define the graph H such that it is the graph G without the vertex X. And let pi H and sigma H be the orderings from UH and VH from pi and sigma respectively. So if the ranking G pi sigma is not equal to the ranking H pi H and sigma H, then they differ by an alternating path starting in H. Let X be connected, the proof. Let X be connected to a vertex V by ranking sigma. Now, since V is not connected to X by ranking sigma H, it will be connected to a vertex X dash in UH. We can apply the same logic to X dash as we did for X. Hence proof. Lemma 2. Fix a vertex U in the graph U and let V be connected to U in the perfect matching. If V is not matched by ranking sigma, then U is matched by ranking sigma to a vertex V dash such that the rank of V prime is smaller than or equal to the rank of V. Proof. If V is not matched to U, then that means that U was matched to something better. That is, it was matched to something before, which means it was matched to something of a lower rank. Thus, the rank of V prime is smaller than or equal to the rank of V. Lemma 3. Let U be a vertex in U and let V be connected to U in the perfect matching. We define sigma prime, let sigma prime be a permutation, and we define sigma I to be a permutation obtained from sigma prime with the vertex we remove, and then we put at rank I. So if V is not matched by ranking sigma prime, then for all I, U is matched by ranking sigma I to vertex Vi, where the rank of Vi in sigma I is smaller than or equal to the rank of V in sigma prime. Proof. Let M be the ranking sigma prime and let Mi be the ranking sigma I. By lemma 1, if M and Mi are not identical, then they differ by an alternating path. Because the alternating path is monotone, Mi matches U to a vertex Vi, such that the rank of Vi in sigma I is smaller than or equal to the rank of V prime in sigma I, where V prime is matched to U in ranking M. We also have that the absolute value of the difference of Vi in sigma I and V prime in sigma prime is smaller than or equal to 1. By lemma 2, the ranking of V prime is in sigma prime is smaller than T. Thus, the rank of V prime in sigma I is smaller than T plus 1, which means that rank of V prime in sigma I is smaller than or equal to the rank of V prime in sigma I in sigma prime. Lemma 4. Let xt denote the probability that a vertex of V over sigma of rank T is matched by the algorithm. Then 1 minus xt is smaller than or equal to 1 over n times the sum of all probabilities from x1 to xt. Proof. Let V denote the vertex V, which has rank T. The probability that V is not matched by the algorithm is 1 minus xt. Let U be such that V is matched to U by the perfect matching. And we also define the set RT minus 1 to be a subset of U such that the vertices of U which are matched to by the algorithm with the vertices of V which have a rank less than or equal to T minus 1. Hence, the expected number of elements in RT minus 1 is the sum of probabilities from x1 to xt. Now we take a new permutation sigma prime from sigma such that we choose a vertex V prime from V uniformly at random. Take it out and put it at rank T. Let U be such that V prime is matched to U in the perfect matching. Hence, by lemma 4, if V is not matched by ranking sigma prime, then U is matched by ranking sigma to a vertex V double prime such that the rank of V double prime is smaller than or equal to T, which means that U is an element of RT. The event U being an element of RT has a probability, the number of elements of RT upon n. Taking expectations over sigma, we get 1 minus xt is smaller than or equal to 1 over n times the sum of probabilities from x1 to xt. Now that we have proved all the lemmas, we shall move on to the main theorem. The theorem. The ranking algorithm has a competitive ratio of 1 minus 1 over n plus 1 to the power n, which is asymptotically 1 minus 1 over e. Proof. We rewrite lemma 4 as st times 1 plus 1 over n, which is greater than or equal to 1 plus st minus 1, where st is the sum of the probabilities from x1 to xt. Note that our performance is Sn because it is the sum of all probabilities. Now we need to consider the worst case, that is when Sn is minimum. This shall occur when all our inequalities are equalities. By induction, we get that St is equal to 1 minus 1 over n plus 1 to the power s, where s goes from 1 to t. This in turn is equal to summation of n over n plus 1 to the power s from s equal to 1 to t. Using the geometric progression formula, we get that St is equal to n times 1 minus n over n plus 1 to the power t. Now we should find the competitive ratio. The competitive ratio will be the limit of n times 1 minus n over n plus 1 to the power t to the power n upon n as n tends to infinity. This is equal to the limit of 1 minus n over n plus 1 to the power n as n tends to infinity. Note that n over n plus 1 to the power n is the reciprocal of 1 plus 1 over n to the power n, which is equal to e as n tends to infinity. Thus, our competitive ratio is 1 minus 1 over e. Conclusion. We have proved that the ranking algorithm for online bipartite matching achieves a ratio of 1 minus 1 over n plus 1 to the power n, which is asymptotically 1 minus 1 over e. Possible extensions. We can try to create more algorithms and analyze the competitive ratio. Thank you.
Very nice presentation, Raghav. This is not an easy topic to present because this requires a lot of prerequisites, which most of you wouldn't have. So this requires a lot of work. So I really appreciate how much work you have put in this presentation. What I would suggest you to do when you're presenting is when you talk about online bipartisan matching, you should first talk about why this is very important. You know, why this matching is very important. What is the unique feature of this matching, because of which this is considered to be a useful mechanism? And then, because that will help you to think about why people thought about this algorithm. I really liked your extension that you mentioned, come up with more extensions that can help to find out the competitive ratio and compute their competitive ratio. So you did a very good job in explaining the extension, but I couldn't see the motivation why we should learn this, and that will help me to think about more algorithms. A couple of small things. You were trying to hover the mouse when you were reading, so
Yes, sir.
avoid doing that because that mouse movement is little distracting for the audience. I know what you are trying to do. You are trying to help us locate where you are,
Yes, sir.
where it is happening, but don't do that. That's I mean, it's hard. It will come by practice. That's not a very big thing. And when you say A dash, it's A prime. So try to
Yes, sir.
use that lingo because that's what people are more used to. Okay.
Okay, sir.
But brilliant job because this is not an easy topic. This requires so much of prerequisite. I'm pretty sure that anyone who is trying to read this paper will have to put in so much effort. So I think disproportionately your paper required a lot of effort. So kudos with that.
Okay.
And I really liked the effort that you have put in and the presentation style or the ease at which you presented. So very well.
Thank you, sir.
And I'm so sorry I joined late. There was some confusion in my mind about the timing. I thought that it's at 2 p.m. today, not at 11:30. So I'm very sorry that I joined 15 minutes late, and that is what has resulted in this extension by 15 minutes. So I apologize for that. Sorry. Manu, are we done for the day? Can we close the meeting?
But the office hours starts again in 30 minutes, especially if they have a lot of homework today. I think 3 or 4 assignments.
Wait, isn't the office hours at 2 p.m.?
Yeah, it's 1 right now, so we're going to keep the meeting on, and everyone could go for lunch and then come back.
But they have to come back by 2, right? Or 1:30?
No, today 1:30 because there's a lot of homework, and then the professor just sent me one more homework to
Oh
assign.
my god, I am still doing a lot of homework.
Okay. And Dr. Tyler's session is at 4.
Yeah.
Okay. Sorry. Then please have your lunch. Sorry for my delay. Even I'm feeling worse now. Okay. Bye.
Thank you, sir. Bye, sir.
Thank you,
Yes,
sir.
sir. Thank you.
Thank you, sir.
Thank
Bye,
you.
sir.
Bye.
Thank you. Bye.
So everyone just stop your video and mute yourself, and then eat lunch and come back.
We'll just
found-
let.
Yeah, and another thing, everybody, have you filled the form?
No.
Oh, yeah, wait, I'll fill it. Sorry, Srinandan.
Yeah, it's fine. Just fill it up as you eat.
Can I finish lunch and then fill it up?
Yeah, okay. You finish lunch and then you fill it up. It's fine.
Yeah.
Thank you.
And by the way, Jayaditya, I've managed to find the answer for first 4 problems. But 5
Even
and-
I did. 5 is also very easy. It's just Catalan numbers. I'll tell you what that means after lunch.
Okay. And 2, an ingenious manipulation required. Anyway, bye. Okay, I'm not leaving. I'm just AFK.
Yeah, fine. Now I'm gonna go on mute and eat lunch.
Is any of you back online? The officer
Yes,
is gonna.
Yes.
The officers will start in 8 minutes.
Hello.
Hello.
And someone is there.
Hello, I am there.
Hello. I am there.
You could have just unmuted Jayaditya.
Hello.
What do you mean?
Yeah, you were explaining to me the problem one day. Can you continue?
Oh yeah, sure. Okay, please. Yeah. Okay, wait.
Could anyone tell me, like, has anyone solved the first and second problem of AKSL's second homework?
Yes.
Yes.
Yes,
First 5 problems.
me too.
Wow.
Okay, so we will give the solution because you want to give the solution or this thing?
Should I give?
I'll give the solution to the first problem. Okay, fine.
Yeah,
The hint.
I'll give the second.
Yeah, let's do that. You know, you don't just think maybe.
I'll give.
Basically, for the first one, you need to use this identity. M plus n choose R is equal to summation of M choose R. R minus K n choose K.
And you should use that to prove this, right?
Exactly. Yeah.
Okay. I'll try that. I have not tried that yet.
Okay.
That
Swasti.
works.
Yeah. So Swasti, should I tell you the solution? You wanted it now?
I'll try it for 5-10 minutes and then
Use this
Okay.
identity.
tell me.
Okay,
That
you can
literally actually works.
basically. You remember I told you you need to you can try substituting M and minus Y.
Yeah.
X and minus Y. Yeah, I think so basically Siddharth did that and he got it.
Okay. Yes.
And so did
okay.
Raghav. Okay, yeah.
Yeah, for the second ones, you need ingenious manipulation, but that can be solved.
Exactly.
Piece of cake.
Ingenious manipulation. You just need to do small kind of a multiplicative recursion thing and then you'll get it.
No,
Yeah.
you need ingenious manipulations.
For the second one,
Yeah.
I did it in a sec after I got the first one.
Yeah, the second one seems easy if you get the first one.
It's basically you have to remove what you don't want.
Exactly. Yeah.
And also one small you can't just remove. You have to do one small change and then remove.
To simplify my solution, Jayaditya, could you please allow me to annotate?
Oh yeah, sure. Wait. Open a new slide and enable annotation. Okay, yeah, you can now.
Annotate. Now, what I basically did is, so I tried to like replace all of the stuff that wasn't important to the problem. So what I did was -1 choose. I am doing that only now.
You want me to write Siddharth?
No, this I am writing like this. Look, I just did like that.
Oh, what did you do?
I put them both under the big S to make my life easier.
Okay, you wrote wait. Okay.
Substitution.
Yeah.
Euler never met a substitution he didn't like.
Okay.
But how is this substitution going to help you?
Nothing. It just like it doesn't help at all. It's just you don't have to keep on writing that.
Bro.
Okay, but you do need the -1 afterwards in the end.
Actually, after S you have to like blow it all up at the end.
Yeah.
Okay.
Yeah, we have to like blow it all up, and yeah, to get you can pretty much get the answer by multiplying by 1 and then dividing by y on both sides.
Exactly. Yeah.
Why are you multiplying by 1?
Hey, what? No, it's correct, no?
You're multiplying. You're actually multiplying by y plus
1
I
upon
over
y.
y plus I. You're
Yeah.
actually multiplying by y plus I over y plus I. can
Okay.
Yeah.
cancel.
Okay. But they haven't.
So you're
Okay. Are you solving the first problem or the second problem?
The
second.
second problem. Basically,
Mm.
what he means is that
Oh, do you
okay,
mean y plus I over y minus over y?
you basically just do one. He means okay. Wait. Uh, this thingy is just equal to y plus I minus 1 factorial into something. So you can just derive that from here. You can use the first result to get the second one.
Yeah. Okay. Just yeah. Okay.
What's the formula for minus A choose B again?
Yeah,
you
this is
want
Siddharth. Yeah.
Finally, someone wants me. The formula for minus A choose B is minus 1 to the power of B multiplied by A plus B minus 1.
Okay, do fast now. Choose.
Choose B.
Okay.
Okay, thanks.
That now it's easy.
Yeah, now just crank through all the arithmetic.
Yeah.
By the way, why did I say cranking through?
I don't know what that
I don't
means,
even know
first
what the
of
word
all.
means.
Exactly. Same thing, Raghav. What does that even mean?
Cranky people.
Cranky people.
Maybe he means like this, blasting through the arithmetic part.
Okay.
Yeah, blasting through the arithmetic.
Okay.
By the way, does anyone know what this is?
What is?
Oh yeah, it's the thing for a game. What do you call it? What's that game called?
Pac-Man.
Pac-Man.
Oh yeah,
Yeah.
Pac-Man. That's Pac-Man.
Yeah, he eats away and the ghosts try to eat him, and that very weird.
Yeah. It's a
Yeah,
very fun
weird
game.
game.
Actually,
It's
shall I
not
tell you,
weird. I like that game.
this is not
I
Pac-Man.
know, but it's so like I can make like there is a interface
not-
where I actually
not-
hacked into that game.
This is not Pac-Man. This is Pinkman.
Bro, stop.
Or how about a Pac-Man? How to do that vanishing arrow?
Oh, it's easy.
That's just a highlight.
Wait, I'll tell you. Go to, well,
Go
you
to
can
the
see,
annotation, but there's something called highlight.
no, it's called vanishing pen. Go to the thing next to the stamp.
Only the presenter can do it, I think. Only the presenter can do it.
Okay, got
No,
it.
but Siddharth did it and Jayaditya is sharing the screen.
Oh, did he?
Yeah, Siddharth drew the Pac-Man, right?
No, but I erased it.
Yeah, Siddharth drew the Pac-Man.
Okay, here's the Pac-Man.
The vanishing Pac-Man.
There you go.
And look, it's not gone. Hey, don't erase. Don't erase.
Gone. Okay, question mark. I'll just draw it.
Look, this is.
Wait, how?
Lord.
Stop it. What the hell?
Where is it? Where is the vanishing text?
It's gone.
We can do it. I can't see it either.
Even where is even the option to do the vanishing text?
Only the person who's screen sharing can do vanishing text.
But Jayaditya is screen sharing and Siddharth did it. Okay, anyways, let it be.
Oh, you need an updated version. You need an updated version.
I have the avatar, so it should be updated.
Oh, what? Maybe. Oh, wait, no, Siddharth also has avatars. Okay, I'll look into it.
Hello. Wait, you are recording this? Should I stop recording?
It was recording from the presentation.